The magnetic field force on a current-carrying wire. A magnet exerts a force on a current-carrying wire. This was shown earlier when we were considering the force on a charge. And since a current is just a number of charges moving through a certain area in a certain amount of time, you might expect there to be a magnetic field force on a current-carrying wire also, because again, it's just a movement of charges. So if you look at this horseshoe magnet here, you have a north pole and a south pole. So you have the magnetic field going from north to south. I have a current carrying wire here. And again, recall that a current carrying wire, it's the direction that the positive charges are moving. So if I were to use my earlier rule about charges, they're moving this direction from right to left. So I would put my 4 fingers in that direction. I would then curl my fingers until they touch the palm of my hand in the direction of the magnetic field, which would be down in this case, and then I find my thumb pointing out of the page, and that gives you the direction of the magnetic field force. To find the direction of the force on a current-carrying wire, we use the right-hand rule again. And in this case, we put our 4 fingers of the right hand in the direction of the conventional current, which of course is the direction that the positive charges are moving. You then curl your fingers into the direction of the magnetic field until your fingers hit the palm of your hand, and your thumb will now be pointing in the direction of the force. Earlier when we dealt with wires, we used our thumb first. We put the thumb in the direction of the current, and then our fingers, as they curled around, would describe the circular magnetic field. So the difference there, here, when you want to find the force, okay, you start with your 4 fingers. So 4 fingers find force. That's a kind of cute way to remember it. And then if you're finding the magnetic field around a wire, then you put your thumb in the direction and your fingers will curl around in the direction of the magnetic field. The magnitude of this force depends on the current, I, the length of the wire, which is L, and the magnetic field, but again, here's the key part, perpendicular. We're only concerned about the value of the magnetic field that is perpendicular to the direction of the current. Just like earlier on, we just wanted the direction of the magnetic field that was perpendicular to the direction of the moving charges. And once you calculate that out, you get a magnitude, and then the direction of the force will be perpendicular to both the magnetic field direction and the direction of the current, hence it's in 3 dimensions.